welcome back to physics class. So we were dealing with the chapter electric charges and fields, and we have learned many things in the last two classes. So now we have an idea about static electricity, basic properties of electric charge, and Coulomb's law. Coulomb's law which talks about the force between 2-point charges. So here we are going to deal with the force between multiple charges. Force between multiple charges. So Coulomb's law talks about the force between 2-point charges, but here we have a system with multiple charges. So what about the force? Actually, this force is given by the superposition principle. The force between multiple charges is given by superposition principle. And superposition principle states that the total force on a given charge due to a number of other charges is the vector sum of individual forces exerted on that charge by the other charges. Let me repeat. The total force on a given charge is the vector sum of individual forces exerted on that charge by the other charges. See, for example, we have a system with charges Q1, Q2, Q3, Q4 and Q5. Okay, now what about the total force acting on this point charge Q1? That is, the total force acting on the charge Q1 is equal to the vector sum of individual forces such as the force on Q1 due to Q2 plus the force on Q1 due to Q3 plus the force on Q1 due to Q4 and the force on Q1 due to Q5. So this is the idea. In here, individual forces are unaffected by the presence of other charges. That means the force on Q1 due to Q2 is independent of the force on Q1 due to Q3. Also, which is independent of the force on Q1 due to Q4 and so on. So this is the idea about the force between multiple charges. So to better understand this concept, let's consider a system with 3 charges. So listen carefully. Here we have a system with 3 charges Q1, Q2 and Q3. Q1, Q2 and Q3. And here we have to find out the total force acting on the point charge Q1. So what about this force? It will be the vector sum of individual forces such as the force on Q1 due to Q2 and the force on Q1 due to Q3. Okay, so we are going to find out that. So total force on Q1, total force on the point charge Q1. Let it be F1. Since it is a vector, let it be F1. So the total force on Q1 is F1. So F1 is equal to, the total force is equal to the vector sum of individual forces. Here the individual forces are F12, vector F12, that is the force on point charge Q1 due to Q2 plus F13, where F13 is the force on first point charge due to the third point charge. Now from Coulomb's law, how we can express this force, or what about this force? That is 1 by 4 pi epsilon 0 Q1 Q2 divided by R12 square, where R12 is the distance between these 2 point charges. R12 square into unit vector, since this is a vector R12, where R12 is the unit vector. Then what about F13? 1 by 4 pi epsilon 0 Q1 Q3 divided by R13 square into unit vector R13. So here you have to recall the vector form of Coulomb's law. So we can express the total force, or we can represent the total charges Q2 and Q3 like this. Okay. Now we are going to generalize this idea. That is, we are going to find out the force between n charges, or if we have a system of n charges, what about the total force? So, listen carefully. We are going to generalize this concept. That is, here we have a system of n charges Q1, Q2, Q3, Q4, etc. Qn. Okay, so in this case, what will be the total force? So again, the force, total force acting on the point charge Q1 will be, or we can represent it as F12 plus F13 plus etc. plus F1n, where F12 is the force on first charge Q1 due to Q2, F13 is the force on Q1 due to Q3, and etc. F1n is the force on Q1 due to Qn. This is the idea. Okay, now what about this force? That is 1 by 4 pi epsilon 0 Q1 Q2 divided by R12 square into unit vector R12 plus, what about F13? 1 by 4 pi epsilon 0 Q1 Q3 divided by R13 square into unit vector R13 plus etc. plus 1 by 4 pi epsilon 0 Q1 Qn divided by R1n square into R1n unit vector R1n. So this is the expression for the total force. Now we can rewrite this equation, because here 1 by 4 pi epsilon 0 Q1, it is a common term. So we can bring this equation in a reduced form, that is 1 by 4 pi epsilon 0 Q1. That is a common term, so we can take it outside. 1 by 4 pi epsilon 0 Q1. Then here Q2 divided by R12 square into unit vector R12. Then what about this force 1 by 4 pi epsilon 0 Q1, which is already there. So the remaining terms Q3 divided by R13 square into R13 unit vector R13 etc. plus Qn divided by R1n square into unit vector R1n. Now we are going to bring this expression in a reduced form. So listen carefully. Here Q1 by 4 pi epsilon 0, that is a common term. So Q1 by 4 pi epsilon 0. Here listen carefully. I am going to write this expression as summation I equal to 2 to n Qi divided by R1I square into unit vector R1I. Listen. Here when I equal to 2, here comes Q2 divided by R12 square into unit vector R12. That is the first term. Now when I equal to 3, we will get the second term, that is Q3 divided by R13. So each time when we are substituting for this I, we will be getting these terms automatically. So we can bring this expression in a reduced form, or we can replace this expression by this. So this is the total force acting on the point charge Q1 in the case of a system with n charges. So usually, this force is a vector sum of the individual forces, and usually this vector sum is obtained by parallelogram law of vector addition, which you have learned in +1. So that's all about force between multiple charges. And now we are going to the next concept, that is electric field. Here we are going to deal with electric field. Actually, this concept is introduced to explain the interaction between charges. So before defining what is an electric field, let's consider a point charge capital Q, which is placed at a point O in vacuum, and there is another charge small q at a point P and at a distance R from the point charge Q. Okay, so here R is a vector. Now, from Coulomb's law, it is clear that this q will exert a force on small q, and it is given by 1 by 4 pi epsilon 0 q divided by r square. But my question is, how does this force act? Or is there anything in between these 2 point charges? So, definitely there is something in between these 2 point charges, and that is the electric field. So, what is an electric field? It is a region around this point charge, and when we bring another charge close to this will exert a force. This will exert a force. So, this electric field is responsible for that force. So, what about electric field, or how we can define electric field? It is the region around a given charge within which when we bring another charge experience a force. Is it clear? So, the electric field due to the charge capital Q at a distance r can be written as E of r is equal to 1 by 4 by epsilon 0 q divided by r square into unit vector r. So, from this expression, it is clear that this electric field is a vector. Here also r is a unit vector. So, electric field is a vector. Also, this is a function of position. That means electric field varies with position. Electric field varies with position. Now, what about the force between these 2 point charges? That is, it is given by Coulomb's law. So, F is equal to 1 by 4 pi epsilon 0 q divided by r square into r cap. So, listen, what about this term 1 by 4 pi epsilon 0 q by r square? That is the electric field. So, we can replace this term by E of r. So, F of r is equal to E of r into Q, or simply F is equal to Q into E, where F is the force, Q is the charge, and E is the electric field. Now, what about electric field E? E is equal to F divided by Q. E is equal to F divided by Q. So, this is the expression for electric field. Now, what about its unit? Here, unit of force, that is Newton. Then what about the unit of charge? Coulomb. So what about the unit of electric field? Newton Coulomb raised to -1. Newton Coulomb raised to -1 is the unit of electric field. Now one more thing. Listen, when this Q is unity, that is 1, when this Q is unity, what about the electric field? It is exactly equal to the force. Or in other words, electric field is equal to the force. Electric field is exactly equal to force when the charge is unity. So, how we can define the electric field intensity? Electric field intensity may be defined as the force experienced by a unit positive charge. Force experienced by a unit positive charge. Is it clear? So, this is the expression for electric field. Now, listen. Here capital Q, which is producing the electric field. So, capital Q is known as the source charge, which is producing electric field. So, capital Q is known as the source charge. And what about small q? Which is used to test the effect of source charge. So, this small q is known as test charge. Actually, this is an imagination. It will be always a positive charge. So, what about the sign of a test charge? Positive. So, we already said that electric field is a vector. Also, this electric field is a function of R, or this electric field depends on position. That means electric field varies with position. So, since this electric field is a vector, what about its direction? Listen, for a positive source charge, the electric field will be directed radially outwards. Electric radially outwards. And for a negative source charge, the electric field will be directed radially inwards. Electric field will be directed radially inwards. So electric field is a vector. Also, it is a function of position. So function of position means at equal distance from this point charge. That means at these points, the magnitude of electric field will be same. Again, these points, these are at equal distance from this source charge. So again, at these points, the magnitude of electric field will be same. So that's the idea about electric field. So now you might have understood about the importance of electric field. So electric field, which talks about the interaction between charges. Also it explains the electrical environment of a charge. So that's all about electric field. Now we are going to talk about electric field due to a system of charges. For this, here we are considering a system with charges Q1, Q2, Q3, Q4. Now suppose we have to find out an electric field at a point P, and which is at a distance R1P from the charge Q1, at a distance R2P from the charge Q2, at a distance R3P from the charge Q3, and R4P from the charge Q4. Okay, so now what about the electric field at this point due to these charges? So of course there will be electric field E1, E2, E3 and E4. So what about the total electric field at this point? And this is given by the superposition principle, and according to superposition principle, the total electric field at the point P, E of R is equal to E1P plus E2P plus, if there are n charges, then etc. ENP. Okay, now what about the expression of this electric field? That is 1 by 4 pi epsilon 0 Q1 divided by R1P square into unit vector R1P. Here 1 by 4 pi epsilon 0 Q2 divided by R2P square into unit vector R2P plus etc. plus 1 by 4 pi epsilon 0 Qn divided by Rnp square into unit vector Rnp. Now we can rewrite this expression as E of R is equal to 1 by 4 pi epsilon 0. That is a common term. So 1 by 4 pi epsilon 0. Listen, summation I equal to 1 to n. I is equal to 1 to n Qi divided by Rip square into unit vector Rip. Listen, summation I equal to 1 to n Qi divided by Rip square. So when I equal to 1, we will get Q1 by R1p square. When I equal to 2, we will get Q2 by R2p square. So where 1 by 4 pi epsilon 0 is a common term. So this will be the expression for the total electric field at the point P. So the total electric field at the point P due to these charges is the vector sum of electric field at this point due to individual charges. So this is the idea and this is the expression for total electric field. So that's all for today. So today we have discussed many points like force between multiple charges, the concept of electric field due to a system of charges. So hope you might have understood all these things. So we will come with a new topic in the next video. So if you have any doubt means once again go through the video or contact through my WhatsApp number. So bye.